what is actually the technology? What is vibroacoustics and acoustic emission sensing? I know that Alfredo has a little bit better picture and depiction on this one. I want to just go a little bit into the history. Acoustic emission is actually an old technology. It's was mainly used in the past for non-destructive testing, and it basically listens to things that happen, so transient informations that happen, stress-related things like in metals or in bearings or all kinds of other things. It's actually nothing completely new. Um, that also has been used in aircraft, in big mechanical devices, in vessel sensing. So in composite materials like carbon structures, just to see wear and to hear, to listen to wear and tear, and to basically get information that has to do with the material properties. Now, basically, the vibroacoustics that we use in our context is the interaction between an instrument and a tissue. And like for example, when you put a guide wire or a needle or a trocar or something else onto into the body and onto tissue, it will work actually as an acoustic waveguide. So you'll be able to use that as a transfer medium for anything that happens between the tissue and the tool on its way down or in front of it. And I'm very happy to say that, that group with Alfredo, Axel Böse, and myself, we have actually started using that as like the first group in really formalized in different applications in medical interventional devices. And I'll show some examples of that. What the advantage of that is, if you put a sensor on the outside end basically of the device, there is no modification necessary of that sterile instrument. You can use whatever you have already in place. With that, it is rather low cost, and it's image independent, and it's also instrument agnostic. So it is, you don't need to have a special device. Now, there's a lot of alternative technologies out there where they put this. I mentioned that before. Different types of sensors at the front or in between the front end and the proximal end. Like for example, fibergrad grating for sensors or piezoelectric arrays. But all of these must be integrated. They basically are an active device. You have to provide it with electricity. It must be sterilized, and it is with that complicated and costly. So this is like the general principle of that. You basically stick the needle in, and you want to guide that needle, for example, towards the target structure. You have a tip in the front, normally a sharp tip, and you go through different types of tissues to actually reach the target tissue. The sensor, which is an acoustic sensor, so it could be a microphone, different technologies that you can use for that one, will basically pick up that signal that is generated at the tip, and also we have to say at the partly obviously comes from the shaft. There's some signal processing involved, some filtering involved, some extraction, some advanced signal processing, and then we subsequently use artificial intelligence to actually extract meaningful information and be able to detect certain events and maybe even characterizations. I have to say, I mentioned it already, there is, of course, an interaction of the signal that happens basically during, when you put the needle in, and initially the dominant information that you get will be from the tip, but there will be additional information that you pick up on its way that basically derive and come from the tissue passing through. But we are, we are finding ways now of how actually to compensate for that. There is some prior knowledge involved. There's other things like also we use advanced machine learning for these ones. So we are slowly getting it that basically whatever we receive and whatever you can extract and show is what happens in the front. A little bit of to the frequencies that we use. So there is different types of frequencies. All the way on the bottom right, you see that that's basically what you normally use from an ultrasound system. That's also acoustic information, acoustic waves. It's an active send of information and then a receive of information of acoustic response, basically of tissue. That's in the order of megahertz, so million waves per second. What we are looking at is much more in the lower frequency range. So it's not so much in the physiological one, even though we are listening to heart and to flow sounds. That's some of the acoustic information that we use, but mainly it is in the lower frequencies up to maybe 10 kilohertz. That's what we use, and that's not typically a frequency that you would associate with a human being, but it is an information that you can extract from an audio signal using advanced signal processing methods, and you can actually every signal can then be cut down into individual frequencies. What do you need for this? We need a microphone. Typically we use contact microphones like MEMS microphones or piezo microphones. We also have initially tried even some stethoscope setups before. I show you a picture of that one. And we're currently working on optical and magnetic sensors as well for basically picking up vibrations that are that can be detected on a needle or device shaft. You need signal processing, classical features, classical signal processing methods. As mentioned before, we don't want to be too technical, but it is quite technical, particularly when we talk about frequency domains. We'll then use some deep learning approaches, and we'll try and actually to do a generative, to generalize the information, which is rather difficult and quite complicated. So we still have to work on that to actually get to a generalized information about what could be the specifics of one particular tissue. So it's not a very simple thing. There is obviously this is an AI created image, so sometimes you have to say that, but most people actually understand it these days. That AI can do things significantly better than I could draw with my hands, and probably also looks better. So what we have done in the present and past was to look at needle access, laparoscopic, so putting the sensors on laparoscopy systems or endoscopy systems. There's also other teams, particularly at the Technical University Munich and others who look at orthopedics, at drill breakthrough detections. We're also looking at that's what we're working on right now at like advanced technologies where we can actually we can obtain an acoustic fingerprint and be able to actually look at behaviors, acoustic behaviors, and acoustic information of different tissues and be able to then subsequently identify them. We need to combine that, probably that acoustics. I also have a picture on this one later on with some other sensory information. And we want to put it obviously on robotic systems because we believe that some of the acoustic information that we can obtain is a derivative or is at least an indication for palpation and for pressure sensing that you can then subsequently transfer again to the surgeon. Yeah, and there's other things that we can do in the future that hopefully will get you excited about, and that scientific community will work together with us on creating particularly safety information for robotic assisted surgeries and some other optical and visual and predictive overlays. I want to show you quickly some images that are done from an acoustic emission point of view. You basically use a sensor, and in this case, it's a carotid flow sensor. We just put it on here, and you see that we have a raw audio signal on the top, but what we're really looking at is the frequency information. So what is the dominant frequency in that, and what is the most intensive signal per frequency? And that is, we have actually shown that is a biometric information. So every one of us has a unique carotid flow, which then also shows that if there's a change to your flow, there must be a reason for it. So maybe, for example, stenosis. So currently we're running a clinical trial on being able, or on whether we are able to actually detect stenosis and even be able to quantify stenosis. And I can say that much already. Yes, we are able to do that. So at least on a small population, I think we have used about 30 individuals that has been proven to work. We now have also tried it out on knee sounds, on joint sounds. So they're very interesting when you go up and down, basically in your knees and back out, that there is obviously sounds that are emitted by the knee that could be used to actually, maybe relax or relieve the menisci or other segments that are maybe particularly demanded. And we are now trying out on whether we can actually use that for measuring muscle sounds and other things. So that's just the acoustic emission part. I want to also show you some acoustic emission that is quite exciting. What we try to do, that's actually some of the work that Katharina Stick is on the call here has done in Krakow. We have set up basically a flow phantom, kind of like simulating a cardiac pulsation flow, and use the needle. You see the number one, that's the sensor attached to the needle, to basically get close to a needle, then have the needle in rest and just basically listen and hope that we can hear or can get information on whether we get closer to that pulsating vessel or not. And we try that in different rows away from the pulsation and then getting closer and being further distant to the sensor. And with that really relatively simple setup, we have shown that it does work. I mean, it is a very, very weird curve, and the curve is actually, that's the surprising part about it. The closer you get with the needle, the lower the signal is, the less intensive the signal is. The further you are away, the more intensive it is. There's probably explanations for that, but we want to verify that more. But in general, you have at least an orientation. Now, this is a simple needle, a simple sensor, and a very rudimentary setup. It should just show that there is a possibility to actually use it also as for directional information and for getting closer to a pulsating vessel. That's again not vibroacoustics, that's acoustic emission. We use the whole thing that's now getting to the vibroacoustics part as trying to measure temperature. Now, why would anybody want to measure temperature? I think there's plenty of reasons and applications for temperature measurements inside. When you do thermal applications, laser applications, or hypothermia or hyperthermia applications, that you need to know roughly what the temperature is of the tissue. You can, of course, stick another needle in there, or two or three or four, and then it's not really minimal invasive anymore. So you have an application needle doing the therapy, and then you have several subsequent needles that are actually measuring temperature. So the idea was, can we actually, because we know that tissue will change with temperature, can we actually use the information and extract a temperature profile from it? So again, a simple setup that we use two different foams, all about 1.5 centimeters thick. You see that there is a different porous sizes in there. And we basically, when we stick the needle in, we pick up the sound that the needle makes when it actually crosses or touches these basically hollow environment. We filled it up with water and basically tried to extract the information, the signal, and put it into a machine learning program. So this is what the signal roughly looks like when you go in and then move forward and move backward. This is the spectrum you get. The MEL spectrum, so it's a frequency spectrum, and up there is the raw signal. And when you put this into a machine learning program, you are actually able to extract temperatures in a rather wide band. So the standard deviation is in the order of 3 to 4 degrees. That is, however, because we also used only 5-degree chums. And if you look at on a mean temperature value, it get actually down to 1 or 2 degrees, which is much better. So technically, you can use that even as a temperature measurement tool. I'd be very happy to know from the audience what else we can do with it and how we can actually use it in real applications. So those are open things. Um, there's a lot of other things that we have tried out. I'm not sure if Alfredo goes into more detail on this one. We have used it on robotic systems to basically use it for surface sensing, obviously for needle guidance. It has been shown to work for orthopedic drilling, listening to the sounds there and interpreting how far you are from a breakthrough. And we also have seen teams, that's also the Technical University Munich, working on auditory display and sonification for navigation on this one. So it is used for several different applications. And we just presented even an interesting one where we try to find out on whether you can hear on whether a biopsy needle has a successful basically has successfully obtained some tissue in the needle or not. So basically, you don't have to take the whole needle out again, but you can maybe reposition it. So that would be causing less trauma to a patient. So that can also be done by acoustics and vibroacoustics. The initial work, that's what I'm about to close this presentation up, but that was a very early work we did in 2018 and 2019, where we actually put that on a catheter device, and we moved the catheter into vessels and try to actually analyze whether we can hear what happens at the tip of the catheter of the guide wire. We can listen to that on the outside. And you see up here, we use on the top right to see this. We used a simple stethoscope and attached that basically to the end of the guide wire, and we're then able to distinguish. First of all, you see already on the original signal that there is quite a different signal characteristics between whether you perforate a heart vessel or you kind of like shrub along the vessel or you bump into a turning point, and that you can then cluster that very well and have a very, very good 95% classification accuracy on these three different types of events. And that kind of like stimulated us to go further and to try out other things. Orthopedic drilling, I mentioned it already. That's a very good procedure. It's probably the most advanced use of acoustic and vibroacoustics, and is something that has also provided a very high sensitivity. Again, comes from most from the Technical University of Munich, and is very close to actually being used into a human application. I don't want to go into the auditory display too much. It's a little bit off, from what we normally do, but it is something that is related. And what I like though is the statement here on the right, and I think that's a very important one, is the auditory channel is underused in surgery and would provide probably meaningful low latency information that could complement vision. I think that's an important statement for all the things that we do. Audio is really not overused, on the contrary, is not used at all, but it could provide significant or very important information for the success or for the progress of a surgery, maybe even lead to a higher success factor. Um, we definitely need to combine this with other sensory input. So we have tried now to actually have a micro CT image correlated to the audio information. It's a paper in progress. That's why I don't want to talk too much about it. It has been submitted. There is a preprint available, however, on this one. And what we used here is a Manduka sexta. It's a worm that basically has a diameter of about 10 to 15 millimeters. And we stuck a needle in there, and when different events that were happening while we stuck the needle in could be correlated to using the distance information, could be correlated to the could be correlated with the audio events that happen. So here you see the audio, the frequency profile of the audio information, and also correlate with the events. So that is a very good information, and it's very important that we need to do to really use audio properly. We probably need to correlate that. Not probably, we need to correlate that with real information and also with imaging information to be sure that it works as we planned it should be. So where are we in 2026? I mentioned some of the different concepts before. Most of them, I have to admit, are in research. Most of them are in early stage research, and we have in some of them shown that it would work in a cadaver, but it is not even close right now to being implemented in a real human application. And there are several reasons for that. We need more shared data. We need obviously better hardware that we're working on. That all comes with funding and all comes with people working on that. We need a more robust and explainable AI. And we obviously need to combine the sensors to create a more trustworthy information, a more also visual information, and an information that we can base also autonomous and semi-autonomous robotic assisted surgery on there. I don't even want to talk about regulatory because that is probably still too far away, but it obviously needs to come as well. All right. Outlook, I think if we work on this one more and we hopefully create a more exciting research environment with that, we could certainly, at least envision to use it for robotic assisted surgeries. I think it is one of the sensors that is missing. It's one of the information that can provide additional information and that can actually help to move more towards the direction of semi-autonomous operation in robotic assisted surgery, which is an important thing to democratize health. And a little bit of I think the key takeaways I don't have to go through anymore. I think I mentioned some of those. But as a final one, I want to make a little advertisement for myself, of course, because I wrote a couple of books on health innovation. So if you're interested in that and also my latest book on this one, then I'm very happy if you consider looking at that. Thank you very much. And I hope you will enjoy Alfredo's presentation as well. And then we're open for questions and discussions afterwards. I hope.
Thank you so much, Frib. If you want to promote your books, you could send me email.
Okay.
Okay, so let's start our next presentation from Professor Ilinis. So I would like Professor Frib you to introduce firstly.
Oh, so I was not prepared to do that, but Alfredo, I think I can do this. So I'm very happy to
Yeah, you know me since 10 years.
yeah. So Alfredo was a very interesting person. I don't even I don't want to tell you why we actually got together, but it was an interesting thing because I was working as a professor in Magdeburg, and so Alfredo had a very interesting prof and a very interesting knowledge base, and was very hands-on, I have to say, extremely knowledgeable in signal processing. He's originally from Chile, was an assistant professor there. Then he moved to France. So his French is a hell of a lot better than his German, even though he lives in Germany for a long time. And he has worked as a postdoc in my lab in Magdeburg and has done really great work. He continues to be in Magdeburg now, working for the computer science department, but working basically on the same topics of vibroacoustic sensing. He also has started a company together with Nasila and others from my former gym. It's a company called Surak, Surgical Audio Guidance, which actually tries to commercialize that technology, particularly for early access on a needle or endoscopy system. I hope that was good enough, Alfredo, and thank you for being.
Was perfect. Thank you. Thank you very much. Thank you very much for the introduction. I will share. Okay. So I hope that I share the sound because this is very important. I have a lot of sound in this presentation. So I thank a lot Professor Friede for the introduction. Yes, we start to work together. I arrived to his chair 10 years ago. I didn't have any clue about what surgery was. I was working mostly in vibratory processes, data processing for vibratory processes, quite far away from the surgical area. I was working mostly for earthquake engineering and also monitoring of failures in machines, in machinery, in manufacturing systems, also in aquaculture engineering. Yeah, so I arrived to his chair and I was a little lost with this surgery. But at the end, and this is how everything starts, when we talk about surgery or when we talk about any minimal invasive procedure, we have a lot of vibrations, yeah? And this is what we are trying to monitor here. So what I will present you here, yeah, so I am now researching in this computer science campus here at Otto von Guericke University, and I will present you some proof of concept going from device guidance, mainly needle guidance, or what information we can provide with vibroacoustic for needle insertion procedures, and I will continue towards what we can do in laparoscopic surgery and with a little also of robotics. So let's start. I think that I will pass this slide because really Professor Friede make a very nice introduction and motivation for the area. Yeah, I think that he say everything what I wanted to say concerning the motivation. But there is something very, very interesting, is that vision in general in surgery has evolved tremendously. Yeah, we pass from these very archaic images to these very nice high resolution imagings. We have 3D imaging. Is really today, when you go to the fairs and you see the new imaging systems, it's really like you are inside the body, and it's really, really nice, really high quality. We have hyperspectral imaging, narrowband imaging. So as you see, vision has evolved a lot, and it's understandable because I think that from our five sense is the sense that is more intuitive to understand by the human. Yeah, but we have five senses and only one is really exploited. So the question is, what about the other senses? Yeah, and this is how we came years ago with this vibroacoustic concept in the chair of professor, working together with Nazila Ismaili from Göttingen. Now she's in Göttingen with people from also from Chile. Yeah, so imagine that you have a structure, a tool can be rigid or not. Imagine a needle, for example, or imagine a laparoscopic camera, an endoscopic camera, or a laparoscopic tool. So in the point when the instrument enters in contact with the tissue, in the point of contact, we have a micro vibration that is produced. What is really nice from this vibration is that it propagates naturally through the shaft of the instrument. And this is really, really important. Naturally, that means that we don't need any active components inside the body, any electronic, any cable, absolutely nothing. And we can pick up this information, this signal from outside the body, from the proximal end of the instrument. This has a lot of advantage. One is that we can monitor whatever tool, in fact, with this concept, because at the end we can connect as an add-on system without taking any active components inside the body. Yeah, and what is amazing, what we have discovered in these last years, is that this signal is extremely rich in haptic and navigation information. It's a very complex signal. We have really struggled with the processing these last 10 years, but once that we can manage this processing, we can extract a lot of information that could be provided in surgeries of minimal or minimal invasive procedures. Okay, how this work? So let's take an example with needle insertion. This is a needle insertion in a phantom, to have a gelatin phantom with ink, black ink, like that people cannot really see inside. And inside the phantom, I have some soft tissues, mostly grape. So we will see what happened in this video is that we will point with a bios. No, this is with a spine needle. We will connect the sensor, and I want that you see the full video. So I take the needle. In this case, the needle is connected with the sensor. This is a vibroacoustic sensor that we implement, is connected with the needle. It's true that the way to connect in this case is not realistic, should be connected from the side. It's only as an example. And we switch on the device. So we have the sensor that connects via Bluetooth to an iPad. And now we will start insertion. And you know that in ultrasound, sometimes it's difficult to really confirm that we are inside the target. And look at what happened when we integrate these two modalities. So we see the grape there, and we start the navigation. Yeah, so I hope that you can hear what you are hearing is every micro breakage that the needle made with the tissue. Yeah, so at the end, you can really confirm that you are inside and not only feel it because of the ultrasound image, but you can really hear the breakage. Yeah, this is another example. Yeah, so you can see that the sound of the needle breaking every tissue layer is very clear. And this is the information that we try to exploit. And this is very interesting because interactions are inherent to any surgical procedure. And what we do is to acquire, to transform, and to map these human, many times imperceptible interactions into information that could be evidence for the surgeons. Okay, so let's enter on what we have done for needle-based procedures. We have been working since a long time on two blind needle procedures, cavity targeting, mostly for Veress needle and for spine needle. So let's see, for Veress needle, this is an insertion of Veress needle in human cadavers. This is an old of our prototypes, but the
And then
interesting
from
part
the right side laterally.
is that you will hear when we pass the two fascias,
Okay?
Yeah.
first fascia, second fascia,
Not yet, but now.
Yeah.
and now
Perfect.
then
We
you
can see
enter
it.
to the peritoneum. Yeah. So clearly you can not only the surgeon can feel what he is doing, but he can confirm with the vibroacoustic feedback that we are providing. The same for a spine needle insertion. So this is in a part of a pig. Yeah. So what we have learned is that this technology is very well suited for cavity targets. Yeah. Why? Because a cavity target has very nice parametric structure. Yeah. So for example, here you start to see when the needle start to enter in contact with the tissue, with the fascia, for example, or with the peritoneal cavity, or with the peritoneal layer. Yeah. So the needle start to get in contact, and you have to start to produce a friction between the needle tip and the tissue. Then you have the release. And this part that you see here at the end of the signal is really important, because one characteristic that cavity has is that a cavity is an empty space or a liquid space. And the way that the needle vibrates has a completely different signature than other type of interactions. And this is what we have shown already in two papers. One paper also soon will be there in pig and in human cadavers. The consistency and how stable is this signature that allow us not only to parameterize this, but also to identify and classify it. This is another work that we have conducted in experiments in synthetic tissue. We have here, you can see two type of foams with different densities. We have a first foam that is less dense, where in average the bubbles are separated by around 400 micrometers. And then you have a denser layer where bubbles are separated in average by 250 micrometers. So we wanted to explore resolution of changes that occur in the density for tissue-tissue transition. And what we find is that even if the layers of the structure are very thin, we can detect difference between passing from a dense material to a from a less dense material to a more dense material. What we have also shown here, and we have confirmed the result that we obtained before, is that here you can see, for example, 16 insertions that goes through the cavity, and 16 non-cavity events. And what we can see is that the cavity events, they produce much less frequency than the between foam separation. Why is this? Because when you pass from one dense material to another dense material, you have damping of the needle. And this is why you have high frequency. When you pass from a dense material to cavity, you don't have this damping by the other density. You have a free oscillation that is very easy to distinguish from other type of event. So let's go. This is what we are working also with one of my PhD students. We are working on see if we can detect tissue transitions in ultrasound guided insertion. So what you see here is a phantom, a gelatin phantom, where we put a piece of pig liver with a chicken breast, and we want to see if we can detect the exact moment when the needle passes from the pig liver to the chicken breast. And this is what we can see. I am inserting the needle. This is liver contact. This is the transition. So even if in the ultrasound it's very complex to see this transition, in the vibroacoustic signal is really clear. We have shown in one paper that will be published soon that even when the needle tip is not visible, you can really recover the needle tip by listening this type of transition. Yeah. Okay, so let's pass now to the other type of application that is laparoscopic surgery. So let's think now in laparoscopic surgery. So the question is, what is the potential of vibroacoustic monitoring in laparoscopic surgery? And here we have how the setup works in this case. We have two laparoscopic tools, one scissor, one grasper. So these are the sensors. We can connect to the lure lock that already these tools they have. We switch on. The system recognizes automatically that we are connected to an instrument and also recognize which instrument it is. Because of the ID, we connect to the second instrument. It recognizes that it's connected to the system, it's recognized that it's a grasper, and then it is ready to use. You see the change of workflow is not enormous. Yeah, and then you can start to play with this and to listen to surgeries. But the important thing is not the listening, is what we can do this information. But let's listen to some laparoscopic tasks. Yeah. I will show you some standard laparoscopic tasks. It's important to notice that I am only audifying. Like that, you can hear the task. But again, I insist, you have to think on what we could do with this information. Yeah. So let's start. For example, this is cutting, palpating, suturing. This I like a lot. You can hear all the part of the suturing. Even you can hear the tension, clipping. You can really hear when the clip is correctly put and not tissue separation. So these are different tasks that usually are performed in also electrosurgery. Yeah, you can hear how the tissue cook, and you can hear the different phases of the tissue cooking. Maybe I will show something later. I think I don't have so much time. Okay, so let's now have a look to what we can do with this data. Yeah, a first thing is to automatically identify laparoscopic tasks. This is a work that another one of my PhD students is doing. So we have different tasks. We divided in three main type of tasks: spatial motion. For example, we want to know if the grasper is approaching or is retracting. We have scissor. We have open scissor with nothing, closed scissor with tissue, and we have some also electrosurgery tasks, etc., etc. And let's have a look. Okay, let's for example focus on how two tasks looks when we treat or when we treat tissue and when we do not treat tissue. Yeah. So what you see here is grasping free and cutting free. This means that I am grasping without tissue, and here I am cutting without tissue. Here I am grasping with tissue without tissue, and I am grasping without tissue, grasping with tissue, cutting without tissue, and cutting with tissue. What I did here you can see 100 events of each task this is what we call the envelope of the signal. I placed them in a matrix. So each envelope, I place them in a matrix because I want to see the difference between all these tasks and how stable they are in their dynamics. Yeah. So what you can see here is that each type of task has a completely different envelope dynamic. This is the information that we take as features and that we use, for example, for doing here I wanted to show that this is the envelope for different type of tasks. But yeah, this I want to show you. So here we have the 15 tasks that we were conducting, and many features. We compute many features, but we are observing these features with a feature reduction UMAP scheme plot. And what we can see here, many we can see that the different tasks, they use different spaces in this 2D mapping. And something very interesting, for example, look at here. Look at here. This is what happened when the grasper is retracting and is approaching through the choker. So you can see that both movements, they have different characteristics that we can completely identify from each other. Look at what happened here. What you see here, this is cutting, but without tissue. And this is when we cut with tissue. Yeah, you have I think that three different type of tissue here. So what we can show here is that with these features, we can completely know when the scissor is cutting in tissue, and even you can also see some kind of clustering between the tissues. Yeah, the same for grasping. What you see here is when the grasp is, I think that this grasping open, grasping closed, and this is where the grasp close with tissue. Also, you can see that the behavior of the grasper without handling tissue and with handling tissue is completely different. Yeah, I have a lot of other examples. Also, we can classify, for example, when we palpate different tissues. Yeah, we are palpating here bone, fat, muscle, skin, and liver. And yeah, this is the spectral characteristics of each one of the palpated tissue. And the vibroacoustic signal tells a lot of information. For example, when we palpate bone, this is mainly high frequency because it's a hard tissue. And when we palpate the other tissue that are softer, they have less frequency components. Something that we can see here, look at the difference between liver, skin with respect to muscle and fat. Yeah, muscle and fat, they have a wider spectrum. What tell us this? Tell us that muscle and fat, they are less heterogeneous tissue than liver and skin. So the vibroacoustic signal can tell us a lot of information of the mechanical properties of tissue. And this is how we can take these features and we can identify each palpated tissue. Yeah. Yeah, this is another thing that Professor was showing, Professor Free was showing with the needle. We have done this with the grasper, the same kind of setup. We have a kind of emulated vessel, and we wanted to know if we can hear these vessels even if they are 2 centimeter depth. What you see here is the signal. The signal is really ugly, but if you dig in the signal, you can find the periodic part of the signal, and you will hear, you can even audify these pulsations. So imagine it's like you can transform your tool in a kind of a Doppler using vibroacoustic. Yeah. And this is what one of our most recent research, we wanted to know if we can detect inclusions in soft tissue, think, for example, in liver tumors. Yeah. And we tested, so we have synthetic tissue where we don't have inclusion. Then we have an inclusion at 12 millimeters and one inclusion at 20 millimeters. So, sorry, the diameter of 12 millimeter inclusion and the diameter of 20 millimeter inclusion. And also, the vibroacoustic signal can give us when we have an inclusion and when we don't have an inclusion, and also can be able to detect the 2 different sizes of inclusion. This opens a lot of perspective for this type of surgery. Yeah, so I think that, yeah, this is the last, this is when we cook tissue. And when we cook tissue, for example, when we coagulate tissue, we can really see changes in the signal that we can associate with different stages of the coagulation. Yeah, this is a work that we are working with the University of Göttingen with Dr. Nazila Ismaili. Soon, I hope that we will have a publication on that that will show more in detail all these results. Yeah, finally, some applications in robotics. For example, you can also hear robotic tasks. You can audify them. You can also train people, not only using the camera video, but also by listening. And we can also detect soft tissue collisions, for example, in robotic arm. We place the sensor in the endoscopic camera, and we can detect clearly when we collide with the soft tissue, and even when we break it. Okay, I think I'm out of time, so I think that it's better to give access to possible questions. Michael, I don't know what do you think? Thank you very much.
Thank you so much. Thanks so much for Professor Elenis' presentation and sharing. So if you have any questions, you could ask this to professors using your microphone, and every audience has been allowed to ask question.
Hello? Hello? Hello?
Hi, Herba.
Hi, how are you?
Yeah,
Hi,
yeah,
Zoe.
that's good.
Is it Zoe, right?
Yes, yes.
Hi,
I
Zoe.
can hear you. I can
Um,
hear you.
Hi, I'm Heba. My name is Heba Taher. I'm Associate Professor Pediatric Surgery at Cairo University. I was really listening to this very interesting two presentations, and I was just really wondering about the future of surgery and how far we are behind. So it means from what you're saying that we surgeons, like I don't recall, I'm trying to remember how we used our hearing in training. Like, yes, I mean, we usually use our tactile sensations in open surgery, even in laparoscopic surgery. But listening to tissue being cut or the clip being applied or all this, even this we feel it. We don't hear it. Of course, this will be great when we are trying to access intrajugular vein, central lines, and all this. But I just want to know, it is not really very clear to me. Is it the computer or the system that is going to still recognize the voice, or the surgeons? Because I can see wavelengths in the second presentation. I can see that every movement corresponds to a wavelength. So every wavelength is being interpreted by the computer, saying, okay, this is being cut, clip being applied, now we are cutting, this is a solid tissue, and this is, or we as surgeons still we need to train how to recognize these voices. It's like trying to learn a complete new dictionary. So if you can clarify this, because still it's beyond our imagination, that would be great. Thank you.
Thank you very much. I don't know, Michael, you want to, or I go first?
Go
Because
first. I will be more generic on what I believe why we need this.
Yeah.
So go
Okay.
first.
Okay, so this is always the question of interpretability and what a computer can interpret with the data and how much you want to leave in or out the surgeon of that. Yeah. What we know is that the information is there. Yeah. Now, the interpretability of the signals is really complex. And it's true that you need a big learning process how to interpret this data. I can be really informatic and I can say, okay, I don't care about the surgeon, I care about the machine, and the machine will make decisions. The problem is that more I take decision capabilities to the surgeon, more difficult is to put for me this device in the market because of all regulatory process and risks. Yeah. If I go to the other extreme and I say, okay, we will give them the information as it sounds, then you will need maybe more training than for the first ultrasound that you have 40 years ago or 50 years ago to be able to take a decision. So what we are basically doing in the group that I lead here in Magdeburg is how to map the information in something more perceivable by the surgeon, that the surgeon still have the huge part of the decision, but with a meaningful information. Yeah, and this is the trade-off of what we are doing today. We know that the information is there, how to provide it. We are exploring visual cues. We are exploring sonification, that is, these are models of audification that are more perceivable by the human. And today we are also exploring tactile. Yeah, so this is a huge question, and Today, I don't have the answer how we will transmit this information because it's a trade-off between what the surgeon can want and what the regulatory process can say about that. Maybe we will have some first answers in the next 2 years or something like that. I don't know what you think, Michael.
Yeah, it is a very valid and very good question. It's translating actually information that you cannot really translate. At the end of the day, some of the audio information you cannot even listen to. You have to filter first and then you have to amplify it. And but it probably the solution is not to have audio information hearable, but to use audio information for determining what happens or what should happen or what will happen. And I'm going a little further than Alfredo because and don't excuse my language and excuse my approach on this one. I don't really care at the moment what regulatory tells me or not tells me. I don't really care on where we will be in the next 2 or 3 years. I'm trying to find out where should we be in 20 years. And in 20 years, I know you've heard about the different types of autonomous levels for robotic surgery systems, right? And right now we are at level 1 or 2 at the most, so we still control everything. The problem with that is you have a very expensive device with a very expensive user who has been training to use the system for years. And the limitation is clearly it's the cost of the system, the cost of the education, and the few people that are available. So we need to go to really make that whole process available, having good robotic assisted surgery. You need to get to a point where there is many more robotic systems out there and the dependence on the user is greatly reduced. This is not what you probably want to hear as a surgeon right now, but at the end of the day, we need to move to a system that is more autonomous, moving up the ladder of autonomy to like 4 or maybe even at some point in time 5, which means they can do things on their own. And then it's not necessary anymore to translate it into visual information. It's not necessary. The computer has to know how to interpret that and what are the next step, what is the conclusion based on that, maybe a prediction even what will happen. So I do believe that this information audio will be one of the information, one of the senses that the computer will need to have to make decisions on its own of what it has to do and what the next steps will be. And there will be an intermediate process where we need to translate it so the surgeon believes it's actually good what they do and the surgeon is still in control of everything. But I think at some point in time, we need to probably that will be used to actually have an autonomous or at least an almost autonomous system available. And then you don't need to hear this anymore. I'm not sure that that answers the question, but I hope at least it gives you some information.
Thank you. That's been very helpful. But still, I think it can be used at least for very limited applications like central line. You just want to know whether you're in or not in. It will be worth
That's
learning a
absolutely,
sound or two.
yeah.
It will
I
be
mean,
worth
these are
it.
those are the things that we're looking for right now too. In all the approach and Alfredo's approach or the approach that one is very simple, yes or no, or it is or it is not information. That is very, very important, and that is already good enough. For example, have you reached the information? Have you reached your target, or is the biopsy needle loaded or not loaded? These are very simple information, but they could be already providing significant value.
Yes, that's true. That's true. And we cannot really fight change. It will come anyways. So we have to accept it and deal with it.
It's a very good approach. I like that. So
Absolutely. I mean, to provide the information directly to the robot for us engineers is easier. Yeah, but I still have the feeling that arriving to this level of autonomy needs a lot of different sensing modalities, and I am sure that vibroacoustic should be one of the sensing modalities that will be part of this, yeah, future. Because at the end of the day, if we think on the cars evolution, yeah, the cars, I don't know, they start in the 60s. How many sensors? Five, six? Yeah, today they have thousands of them, and this is why they can do autonomy. We are really in a very early stage for that. I mean, it's not that I'm not saying that I disagree with you, Michael, about that we will be there, but I see still a lot of work to do. But vibroacoustic will be or has to be one of these modalities.
I fully agree with you. There's
Mm.
no discrepancy with what you said, and I believe. More questions? I guess not.
Thank you. I guess there's no more questions from our audience. And after this webinar, I will end this webinar and cut them. They release this on our website as well as YouTube, so that the audience could see our videos later. And also, we just discussed the acoustic and also tactile. And I would like to have a reminder that in November we have another international webinar to discuss the haptic, the surgical robot from haptic for the operator to robotic autonomy. So I think there is some similarities with our webinar topic today. So if you are interested, we will invite all both of you and as well as Herbert Taher as the guests for our next webinar in November. Okay. So thank you so much. Thanks for your time and thanks for your energy to attend and chair this webinar. And thanks for your excellent presentations.
Zoe,
So,
can I just add
yeah.
something, please, if you don't mind? I mean, I've heard about the upcoming publications. Like, you've mentioned a few publications been published and something, and few are pending. If you can kindly, like after each webinar, you share the publications which were referred to so that we can have a look at, and also share the pending ones. That would be really helpful.
Oh, okay. Okay. Thank
Thank you.
you. Thanks for reminder. So this webinar is over to here. So thanks for your time and energy.
Thank
Thank
you very
you,
much.
Professor
Thank
Prep.
you.
Thank you.
Bye bye.
I don't know
Bye.
if I call the correct pronunciation. I don't know,
All
Professor
good, all good, all
Felipe,
good.
Felipe or Fribe.
Liebe, yeah,
Felipe.
but that's
Yeah,
okay. Yeah.
also Professor Elenis.
Ilanis.
Elanis.
Yeah.
The real one will be Illanes, but okay. But
Yeah,
here in Germany
Elanis.
they call me Illanes. Yeah.
Okay, okay. Thank you. Thank you so
Okay.
much.
Bye.
So,
Bye.
Bye.
bye. Bye.
Bye.